Hello, and welcome to your AP Statistics lesson on Chapter 23, Inference About Means. This is Mrs. Brown, and I'm here with my two favorite doggies, Daisy and Scout, and we are going to talk about means today. Now, we know how to do inference. We know how to create a confidence interval and conduct a hypothesis test about proportions. So now we're going to talk about how to do it for means. The central limit theorem told us that the sampling distribution model for means is normal with a mean of mu and standard deviation of sigma divided by square root of n. So, remember, the scenario is we have this population that has a mean of mu and standard deviation of sigma. And whether we are doing a hypothesis test about the value of mu or a confidence interval about mu, we are trying to estimate mu. So we report back the sample mean of X bar. And we take all those X bars from all the different possible samples of a certain size, and we create our sampling distribution. So the sampling distribution of X bar is going to be centered around mu, and the standard deviation is going to be sigma over square root of n. So to do this, all we need is a random sample of quantitative data and the true population standard deviation sigma. The inference we're doing is about mu. We recognize that we don't know that, but it doesn't really make sense that we would know sigma if we don't know mu. So why is that different than with proportions? Well, proportions have a link between the proportion value and standard deviation of the sample proportion. That's not the case with means. So what we're going to actually have to do is estimate sigma with the standard deviation of the sample, which is called est. And so we'll use the standard error of X bar, which is S over square root of n. So since we're using two statistics, X bar and S, we're going to have more variation in our standard error because of the S, and we now need to allow for that extra variation so that it doesn't mess up the margin of error and p-values, especially for a small sample. The shape of the sampling model also changes. The model is no longer normal. It's still bell-shaped, but it's going to be flatter there in the middle, and there's going to be more area in the tails. So what is the sampling model? Well, it turns out there's a whole family of sampling models called the t-distributions, and they are dependent on the degrees of freedom, which is equal to the sample size minus 1, so n minus 1. This family of distributions was discovered, if you will, by William S. Gossett, who worked for Guinness Brewery in Dublin, Ireland. Empirically, he just found the normal model wasn't really working quite right. And so he came up with the sampling model, which is called Students T, and it's a whole family of related distributions that depend on a parameter known as degrees of freedom. And we write degrees of freedom as a subscript. Anytime you are writing a test statistic T, you include the degrees of freedom with it. It's interesting that it's called Students T instead of Gossett's T. That's because Guinness Brewery wasn't so sure about this newfangled field of statistics and didn't want to have their employees' name, and certainly not the name of Guinness, associated with something that might turn out to not really work out. So Gossett had to publish under the name Student. Okay, so a practical sampling distribution model for means is that when the conditions are met, the standardized sample mean follows a student's T model with n minus 1 degrees of freedom. Our T is going to play the same role as Z does. It's going to tell us the number of standard errors above or below the mean our sample mean falls. So it's going to equal X bar minus mu. divided by the standard error of x bar. And remember, the standard error of x bar is s divided by the square root of n. When Gossett corrected the model for the extra uncertainty, the margin of error got bigger. Your confidence intervals will be a little bit wider, and your p-values will be just a little bit larger than they would with the normal model. By using the t-model, you've compensated for the extra variability in precisely the right way. My apologies if you can hear Scout snoring softly in the background. She is a tired out pup. All right. The one sample t interval for the mean, again, you have to check condition, and then you're ready to find the confidence interval for the mean. It's going to follow the same overall formula of estimate plus or minus margin of error, where the margin of error is a critical value times some either the standard deviation or, in this case, standard error. So we have x bar plus or minus the critical value of t for n minus 1 degrees of freedom times the standard error of x bar. And again, the standard error of x bar is s divided by square root of n. The critical value for a t distribution is just like a critical value for the z distribution. It's going to depend on the particular confidence level. And in this case, the one thing that's new is that it does depend on the degrees of freedom, the n minus 1. Okay, so again, these models are unimodal, symmetric, and bell-shaped, but they have fatter tails and flatter modes. And so as the degrees of freedom increase, though, the t-models look more and more like the normal model. In fact, the t-model with infinite degrees of freedom is exactly normal. So Gossett found the t-model by simulation. He figured it out based on working with tons of distributions and real-world situations. Years later, when Sir Ronald A. Fisher showed mathematically that Gossett was right, he needed to make some assumptions to make that proof work. We will use these assumptions when working with students T. All right. One assumption is independence assumption. And so the data values should be independent. And many times we can find evidence for that by checking the randomization condition. The data need to arise from a random sample, preferably simple random sample, or a randomized experiment. The 10% condition, it applies here. It's not as critical with means as it is with proportions, but we will still check it whenever we do sampling. With an experiment, we don't have to. When a sample is drawn without replacement, the sample should be no more than 10% of the population. That way we can act like the observations are independent, even though there's this replacement going on. There is no replacement going on. All right, normal population assumption. We can never be certain that the data are from a population that follows a normal model, but we can check the following. Now, if they tell us in the problem that the original distribution is normal, that's awesome. If the distribution of the observations is normal, then the sampling distribution will at least be approximately normal too. All right. But if we're not told that, we need to check the nearly normal condition, and the data have to come from a distribution that is unimodal and symmetric. You would check this condition by making a histogram or a normal probability plot of the sample. For small sample sizes, the distribution of the data has to be close to normal. It just has to be. Remember, we're talking about what the distribution of the observations tell us about the sampling distribution. So if we have a sample size of 15 or less, then the observation themselves have to follow a normal model in order for our sampling distribution to be nearly normal. For moderate sample sizes, in between 15 and 30, some people put 40 or so, the T works as well as long as the data from the sample are unimodal and reasonably symmetric. Okay, so we've moved away from it being close to normal. Now you just need a single peak and rough symmetry, and you're good. For larger, greater than 30 sample sizes, the T methods are safe to use unless the data are extremely skewed. We love the central limit theorem. It lets us say that for any distribution with sample size greater than 30, the corresponding sampling distribution for means is nearly normal. Remember, again, I keep emphasizing this because people have a hard time with this concept sometimes. We are looking at the distribution of the sample data to tell whether or not the sampling distribution is plausibly nearly normal. So, in practice, we have our population and we take a sample, one sample of size n, x bar. We look at that sample. If we have less than 30 or 30 or below members of our sample, and then we're looking for clues as what X bar is doing, what the sampling distribution of all the sample means would look like. As long as our sample size is larger than 30, we know that it's going to be approximately normal. If it's smaller than 30, we need to look at the distribution of our sample to make a statement about whether or not it's plausible that the sampling distribution would be nearly normal. Okay, you can find T values by hand. You just have to have an appropriate table. The model is different for each value of degrees of freedom. Because of this, statistics books usually have one table of T-model critical values for selected confidence levels. Alternatively, we could use technology, to find T critical values for any number of degrees of freedom and any confidence level you need. So what technology could we use? Well, for us, we're going to use our CAS, any graphing calculator that has a good statistical package should work, or a statistics program. All right, I'm not going to go over all these ways that are incorrect of interpreting a confidence interval. You might want to read over them. Remember, it's a statement about the population mean, okay? It's not about individual values. And you want to make sure you don't make a statement that makes it sound like the true mean varies. And you don't want to ever indicate that any percentage of samples are going to end up with exactly the same endpoints that we found. Because of sampling variability, the sample means are going to vary, and therefore the exact intervals will vary. Here's what a confidence interval should say. 90% of intervals that could be found in this way would cover the true value. Or make it more personal and say, I'm 90% confident, good to throw in a based on this sample, that the true mean is between 29.5 and 32.5 miles per hour. Making a picture is wonderful. It helps us understand what's going on. It's critical if you have a small sample size and you're not told that the original population was normal. You have a small sample size and you have the picture. In order to satisfy the nearly normal condition, you need to make a dot plot, a histogram, a stem and leaf plot, anything where you can look and see that it's unimodal and symmetric and has no outliers. Alternatively, you can make a normal probability plot to see that it's reasonably straight. So a normal probability plot linearizes data that are normally distributed. So if your data line up in a fairly straight line, that's evidence toward the sample being from a normal distribution, or at least unimodal and symmetric distribution, which then means it's plausible to say the sampling distribution is nearly normal. These are fairly easy to do. The one advantage, making one on the calculator is just as easy as making a histogram or a dot plot. It's just sometimes they're quicker to draw. All right. The conditions for the one sample t-test for the mean are the same as the one sample t-interval. Your null hypothesis is always going to be that the mean equals some value that has been the standard. Our test statistic is the same and the same with our standard error, and we're still going to be using the t-model with n-1 degrees of freedom. When we conduct a test and we decide we have statistically significant evidence, that doesn't mean it's actually important or meaningful. Because of this, it's always a good idea when we test a hypothesis to check the confidence interval and think about likely values for the mean. This is also why it's important for people in all kinds of different fields to have an understanding of statistics. A statistician can tell you whether or not a result is statistically significant, but it takes an expert in any given field to say whether or not the difference that we're seeing is worthy of concern or changing policy. Remember, just like with proportions, confidence intervals and hypothesis tests are built from the same calculation. In fact, they're complementary ways of looking at the same question. The confidence interval contains all the null hypothesis values we can't reject with these data. More precisely, remember, a level C confidence interval pairs up exactly with the two-sided hypothesis test at an alpha level of 1 minus C. You have to divide that by 2 whenever you are looking at a one-sided hypothesis test. All right, to find the sample size you need for a margin of error that you desire, you would go about it very much like you would for proportions. You're going to do your critical value T star with n-1 degrees of freedom times our standard error, S over square root of n. You'll plug in whatever you want for the margin of error. The S will have to come from a small pilot study or be given to you. And since we don't know what n is, we don't know n-1, so we can use Z star as our critical value in place of the T star with n-1 degrees of freedom. So sometimes people are kind of frustrated. Well, that's not going to be exact, and the margin of error won't be exact, and that's okay. With means especially, because the sample size formula depends on quantities you won't have until after you collect the data. Okay, so let's look at some examples. And you'll want to either have your calculator out or look at the table in your book, or both. I would suggest both if you want to know how to find these values both ways. All right, we want to find the critical value of T for a 95% confidence interval with degrees of freedom equal to 7. So if you use table T, find 95% confidence, go to the row for 7 degrees of freedom, and you'll see that T star is 2.365. Or you can just go to your scratch pad and use menu, statistics, distribution, inverse T. You will use 1 minus 0.95 over 2, so 0.025 as the area and 7 as the degrees of freedom. And then you're going to use the absolute value of the answer given. All right, so let's find the critical value of T for 99% confidence interval with degrees of freedom equal to 102. Now, if you look for the row with 102 degrees of freedom, you're not going to find it. So we have to use the conservative Price is Right approach. I don't know if y'all have watched The Price is Right, but the people that get to actually go on stage and participate and everything get there by guessing the price of an object, the closest price to an object without going over. So we will use the closest number of degrees of freedom without going over our desired degrees of freedom. So in this case, 100, and we get that T star is equal to 2.626. All right, we want to find the p-value for T less than or equal to 2.19 with 41 degrees of freedom. One way we can do this is by going back to distributions, choosing TCDF, Since this is a less than problem, our lower bound will be negative infinity and our upper bound will be 2.19. That gave us degrees of freedom. Watch out there because they can give you degrees of freedom or they can give you the sample size. If they give you the sample size, you have to subtract 1 to get degrees of freedom. But in this case, they gave us degrees of freedom, so we put it in just like it is, and we get 0.9828, on and on and on. All right. Hoping to lure more shoppers downtown, a city builds a new public parking garage in the central business district. The city plans to pay for the structure through parking fees. During a 2-month period, 44 weekdays, daily fees collected averaged $126 with a standard deviation of $15. What assumption must you make in order to use these statistics for inference? We must assume that our data are a representative sample of less than 10% of all days. Our sample is considered large enough, n equals 44, that this central limit theorem will apply, so we know our sampling distribution will be at least nearly normal. We want to write a 90% confidence interval for the mean daily income this parking garage will generate. So we put this into our calculator. It's going to ask you how you want to enter your information. Do you want data or you want to enter statistics? We want statistics. X bar is 126. S of X, that's the standard sample standard deviation of your observations, is 15. This one prompts you for N, so you just put in N and tell it you want a confidence level of 0.9, and it will generate your confidence interval, which is $122.20 to $129.80. We're going to interpret it. We are 90% confident, based on this sample, that the true mean daily income for the parking garage is between $122.20 and $129.80. Explains what 90% confidence means in this context. If we found many random samples and continued to use the same methods to produce confidence intervals, 90% of such confidence intervals would contain the true mean daily income. The consultant who advised the city on this project predicted the parking revenues would average $130 per day. Based on your confidence interval, do you think the consultant was correct? Why? Well, no, the entire interval is below $130. Someone suggests that the city use its data to create a 95% confidence interval instead of the 90% confidence interval you created. How would this interval be better for the city? You don't need to actually create it. The city would be more confident that the interval contains the true mean. How would the 95% interval be worse for the planners? Well, remember, whenever you gain confidence by changing the confidence level, you lose precision. So the interval would be wider. It's going to be less precise. So how could they achieve an interval estimate that would better serve their planning needs? Okay, you don't want to just mess with the confidence level. If you want to be more certain and you want to have a more precise estimate, you increase the sample size by collecting more data. How many days worth of data should they collect to have a 95% confidence of estimating the true mean to within $3? Okay, so they're giving us a margin of error that they desire at a certain level of confidence. So we're going to use our formula. We know that we want our margin of error to be 3, and that's going to equal T star with n minus 1 degrees of freedom times S divided by the square root of n. Well, we don't know what n is, so we're going to use Z star. The problem gave us a value for S is 15. So our Z star is 1.96. So let's start off by dividing both sides by 1.96. And then we cross multiply and we get 3 times square root of n equals 15 times 1.96. We divide by 3. We get rid of the square root sign by squaring both sides, and we get 96.04. We always round up, so n is 97. A company with a large fleet of cars hopes to keep gasoline costs down and sets a goal of attaining a fleet of average of at least 26 miles per gallon. To see if the goal is being met, they check the gasoline usage for 50 company trips chosen at random, finding a mean of 25.02 miles per gallon and a standard deviation of 4.83 miles per gallon. Is this strong evidence that they have failed to attain their fuel economy goal? All right, we're looking for strong evidence, and so that means we're conducting a hypothesis test. So, what are the hypotheses? Well, your null is going to be that the mean is equal to what the company has said it always equals, so 26. Um, Now, with fuel economy, you want more miles per hour. So, if you're not keeping the goal, that means that the true mean is less than 26 miles per hour. So our alternative is going to be in the less than direction. So let's check assumptions. We have a representative sample. It does say that it was the trips were chosen at random. So, and it comprises less than 10% of the population, yet it's large enough, n equals 50, that skewness would not compromise the application of the CLT. So it's reasonable to assume that the sampling distribution will be nearly normal. All right, we want to describe the sampling distribution model, a mean fuel economy for samples like this. And so it's going to be shaped like a T distribution with 49 degrees of freedom, with a mean of 26 and standard error 4.83 divided by square root of 50. We're going to find the p-value. You can just do the test straight away. The calculator knows that the null is that the mean equals mu naught, the null hypothesis value, so it's only going to prompt you for the value. So 26, x bar is 25.02, S of x is the sample standard deviation of the observation, so that's 4.83. N is 50. Notice you don't have to divide by square root of 50. The calculator is going to do that for you. So you put the actual standard deviation you're given, and you put in what the sample size is, and the calculator takes care of it. You do need to indicate which type of alternative you have, that mu is less than mu naught. And we get a p-value of 0.0789. Explain what the p-value means in this context. If the true average fuel economy is 26 miles per gallon, then the chance of obtaining a sample mean of 25.02 miles per gallon or less by natural sampling variation is 8%. Well, we consider that to be high. It's greater than 0.05. So my conclusion is going to be as follows. Due to our large p-value, 0.08, there's insufficient evidence to reject the claim of fuel economy of at least 26 miles per gallon. So there is not strong evidence that the company has failed to attain their fuel economy goal. Okay, guys, thank you so much for watching this video. Do the problems to try on your own, and we will go over them later. I hope you have a great day.